In this module, we will start discussing the transport on zero-dimensional or quasi-zero-dimensional devices. Those are mainly quantum dots. In this lecture, we will go over the single electron charging, transport across single electron tunnel barriers, and the observation of single electron tunneling oscillations in single tunnel barriers. When people discuss quantum dots, many times quantum dots and nanoparticles were used synonymously, but they are not the same. Quantum dots are man-made droplets of charge. Those are small nanoscale or microscale conducting regions where quantum effects due to confinement are observed. Nanoparticles could be nanoscale or microscale size material of insulating nature also. These quantum dots in general contain a few thousands of electrons, and the size could be nanometers to a couple of micrometers. So they are always not necessarily nanoparticles. The requirement is you need to observe quantization effects or quantum confinement effects on various electrical and electronic properties. When we talk about quantum dots, you can roughly say that it's a small conducting region connected to rest of the world through a thin insulating region, or we can say for transport in electrical transport language through tunnel barriers. Okay, and if you look at the literature, quantum dots are made by various methods. You can have epitaxial quantum dots where small conducting regions are deposited on certain substrate using epitaxial techniques such as molecular beam epitaxy or MOCVD. Then there are self-assembled quantum dots, and there are etched quantum dots where you define regions, conducting regions by microfabrication techniques such as lithography techniques, and then you remove the material wherever you don't want it and define conducting regions by etching. Okay, and another way to define quantum dots are by electrostatic gating. Here, just as we discussed in one of the previous modules, you deposit gates on a two-dimensional electron system such as two-dimensional electron gas and apply voltages on those gates, and these voltages will confine electrons in a small region in between these gates. Okay, and you can tune this size and shape of this conducting region by tuning the voltages on these gates, and some level of tuning of the size and shape of dot is also possible in these lithographically defined quantum dots too, where you can apply voltages to these gates and you can get some level of tuning the electrical properties too. But here, this is going to give you a completely tunable quantum dot, this technique. So in general, these two techniques are used for realizing tunable quantum dots, whereas these two techniques are not really applicable where you want to tune the electrical properties such as the size of the dot, shape of the dot. These two techniques are not useful. And since this is a transport lecture and we are interested in electrical transport and devices utilizing the quantum aspects in electrical transport, we will mostly be discussing quantum dots of this nature and mostly of this nature, of this kind. because to run currents and voltages through this device, you need leads where you can apply voltages onto the device and take electrons or put electrons into the device and from the device. Okay. So these designs really don't allow you to do that because those are random and you cannot really attach leads to these devices, this material easily. It's almost impossible to some of these structures when the size is very, very small. Whereas this technique naturally will allow you to define leads because you can define leads and you can define the Coulomb dots by in a controllable way using microfabrication techniques. Here also the same method applies. So these are actually voltage tunable Coulomb dots, and this is where most of the experiments that we are going to discuss is done. Okay. So now talking about Coulomb dots, whatever the fundamental physics that we are going to discuss applies to all kinds of Coulomb dots. But I will mention most of these in context of this voltage tunable Coulomb dots. Okay. Now, when we talk about transport is a process where you charge and discharge certain region or certain device. Okay. When I say charge and discharge, what does it mean is you put electron from one side and remove electrons from the other side. Okay, that is the charge and discharge process. That is how transport happens. Now, from basic electrostatics, you know that to add certain amount of charge to certain material with certain capacitance, you need to apply certain energy. That energy is generally called charging energy, which is given by this equation E squared by 2C sigma, where C sigma is the capacitance, self-capacitance of that body. And we know that self-capacitance is a geometrical quantity, which is a measure of its physical size. Larger objects will have larger capacitance. For example, a resistor will have a resistance and also got a capacitance. That capacitance could be of the order of a nanofarad in that range. Of course, that's going to depend on the details, other details such as its actual exact shape and everything. But in general, the capacitance would be in that range. Okay. Now, you have a source and drain region here. Assume that you are going to put an electron through it through a thin tunnel region where there is a really thin insulating region where you are going to add electrons and remove electrons from the other side. Okay. What I am trying to say here is not connected completely with a metal. There is a small region which allows you to put electrons easily, but it is a non-conducting region. Okay. The electrons tunnel through this thin insulating region which separates the source or drain with the material, with the device. Now, in this case, to add an electron or charge or discharge, this is the energy that you have to exert. And you can work out this number. E squared is going to give you, if you work out this number, E square is of the 10 to the power minus 38 and C sigma is 10 to the power minus 9. And you know that this is really, really small. This is almost like 0, very close to 0. It's very, very small, this number, for a large object. But now let's consider one of these material, a Coulomb dot of the size of few tens of nanometer to like a micrometer. Okay. And you can work out its self-capacitance, and to charge and discharge or to transport electrons through the quantum dot. Quantum dot, I would say in general, let me mark it as QD, quantum dot. The energy that is required is substantial because the capacitance part is very small. This could be in autofarads to even lower, femtofarad, autofarad, even lower the capacitance. Okay. And if you work out the number again, what you would see that this charging energy EC could be like millivolt, only milli electron volt. Sometimes it could be even more because the capacitance is actually very small for this. And just to give you a reference, the room temperature is something like 25 milli electron volt. That is the energy of room temperature. That is the KBT. This is the KBT for room temperature. Okay. So if you have a charging energy, say like a milli electron volt, and if you try to run a current through the system, you can easily run even at a really small voltage because the room temperature itself is going to populate or depopulate this region by thermal fluctuations. So you can easily run a current through it. You don't need really high energy. You don't need to apply any extra energy. But that is not the case. The moment you consider cryogenic environments, the KBT term can be very, very low. For KBT for 1 Kelvin is approximately 87 microelectron volt. Say for a 1 Kelvin, and if you have a charging energy of 1 millielectron volt, then the transport is going to show signatures of this charging and discharging process or charging energy. Just to give you a feeling, here I have a table assuming these quantum dots are spherical, which roughly gives you what is the size scale that you require to observe charging or discharging effects at certain temperature. For example, 300 Kelvin, it should be like in nanometer scale. At 77 Kelvin, you need like 15 nanometer. 4 Kelvin, 2 micrometer object can actually show you, and 1 Kelvin, even like a few more micrometer objects can actually show you these charging and discharging effects. These numbers are based on just physical size and the capacitance that we calculate from the physical size. But this capacitance calculation you have to take with a pinch of salt because it's always going to attach some leads, right? That actually can increase its capacitance. So these sizes also will get adjusted accordingly. But this is purely based on the self-capacitance of completely isolated bodies. Completely isolated body in the shape of a sphere. Okay. So in nutshell, what we are saying here is to observe these quantum size effects in transport, one essentially needs cryogenic temperatures. That is because below 50 nanometer, even 50 nanometer itself is actually challenging. You cannot really attach leads to run currents or apply voltages to these devices. So you always require, for any easily realizable size, you always require a cryogenic temperature ranges or cryogenic environment to observe quantum effects in transport. This effect is actually because of the confinement, but it's not purely a quantum mechanical effect. It is an electrostatic effect, but the quantum effects that you are seeing here is because of the charge E is actually quantized. Okay, but we will discuss in detail in the coming slides, but this is just a preamble. Okay, so the take-home message is you need quantum size effects. If you want to observe quantum size effects, you need low temperature environment. Okay. Now, the effects that we just discussed, the charging effects, that is a purely classical effect, but you're observing that because the charge of electron is discrete or it is quantized. It's not really an effect where you are seeing quantum mechanics. Okay. Now, to observe these charging or discharging effects, apart from the temperature, low temperature environment or requirement for a cryogenic environment, there are certain quantum mechanical constraints too, or requirements too. Okay, let's look at conceptually what it is. So, if you are saying that the charging or discharging to certain object, certain solid, requires extra energy, what that means is the charge state of that body should stay stable, it should not fluctuate over sufficiently long time, or the charge from that body should not leak out immediately. Okay. In other ways, the charging energy delta, charging energy EC should be well defined, or charge leak out time, the associated time uncertainty with that energy should be basically low. Uncertain time should be low. That means time should be long. Okay. So, but now let us look at electrically, because these are electrical circuits, but you are going where you are observing quantum mechanical effects. So, electrically, what does it mean by this time uncertainty? So, you have a quantum dot with certain capacitance C sigma. It is connected to source and drain region through certain resistors. These tunnel barriers are actually resistors as well as electrical equipments are concerned. Okay, these resistors R and the C is going to give you a RC time constant for charge leak out. Okay. Now, the energy uncertainty associated with this charge leak out is given by the quantum mechanical energy uncertainty relation, that is delta E, delta T is H approximately. So that is going to give you the energy uncertainty associated with this time is H by tau RC. Okay. And this energy uncertainty should be much lower than the robust energy scale that we are discussing, that is the charging energy. Then only you can observe it. If this energy uncertainty and these are comparable, that means you will not observe it. Okay. To observe this energy delta EC in transport, you need to have this uncertainty in energy should be much lower than this. Okay. So what that means is delta E, the energy uncertainty, which is approximately H by tau RC from here, should be much smaller than EC. That's the condition. Okay. Now EC is E square by 2C sigma. When you substitute this here and rearrange the terms, what you would see is that you have to substitute for RC, tau RC from here. Okay. Now when you rearrange all these components, what you would get is the tunnel resistance requirement, because RC here is the tunnel resistance. This tunnel resistance requirement to observe this charging discharging effect is H by E square, which is basically a quantum mechanical requirement. It's a quantum mechanical requirement. Okay. So, and interestingly, with very, very simple quantum uncertainty relation, without going deep into any mathematically rigorous, we are getting that this is the quantum resistance, quantized resistance value, h by e square, or it is the inverse of quantized conductance value, which we have learned in quantum point contacts and also quantum Hall effect. Okay. So naturally, this term h by e square is popping out just from the quantum uncertainty relation. Okay. So what we are saying here is the resistance or the tunnel barrier resistance through which this quantum dot is connected to the rest of the equipment should be at least h by e square, that is 25.8 kilo ohms. Else, you will not see this charging discharging effects. Okay. So that is the quantum mechanical requirement for observing this charging or discharging effect. Whereas you have already a classical requirement, that is this EC should be far greater than kBT. That's a classical requirement. This is actually telling you that you need low temperature, and this is keep putting a requirement on the resistance of the tunnel barrier. Okay. Now, let's look at the transport across a single tunnel barrier. You require two tunnel barriers for transport. In general, you require two. Okay, one for the source side and one for the drain side. But let's look at the transport across one tunnel barrier first. Okay. So when we say tunnel barrier here, the assumption is there are moderate exchange of electrons happening. The coupling between the two sides, if this is a tunnel barrier, the source side and drain side, the coupling between these two sides is weak, relatively weak. What that means is the wave functions of electrons on either side, which is psi1 and psi2, are not very much affected by this coupling. They are still same. They don't change. This electron states on the source or drain side doesn't much. It's not going to change much by this coupling, by this tunneling process. Okay. So in that regime is what we are going to apply all our, mathematics or all our concepts. Okay. The Hamiltonian in that regime is given by H1 and H2 are the Hamiltonian of the states on either side, either sides, and HT is the perturbation term, or it represents the exchange by tunneling. Okay. So in this specific situation, you can calculate the transition probability or transition rate by applying Fermi-Coulomb rule. Okay, which actually says the rate from initial state to the final state is given by this matrix element, which couples the initial and final state through the tunneling Hamiltonian. Okay, and the delta function EI minus EF. Okay. This EI minus EF says that this is the delta function. So what that means is it is going to be 0 for every other energy. It is valid only for EI equal to EF. What that means is the tunneling actually is energy. During tunneling, the energy is conserved. It's the energy, the two initial and final state should have the same energy. That's what it says. Okay. This enforces the conservation of energy during tunneling. This delta EI minus EF. Okay. The current through the tunnel barrier is given by the charge into the tunnel rate. Okay. And this Tij which we write in short for this tunneling matrix element, psi IHT, psi f, okay, psi TIF, okay, TIF, and this is the transmission coefficient, okay. Now, the premise that we have applied this Fermi-Coulton rule is that the tunneling between the two sides, or tunnel coupling between the two sides is weak. So for large coupling, if there is a lot of coupling between the two sides, the states itself can get modified by interaction in the reservoirs. Then if there is a lot of coupling, then you can have a lot of tunneling back and forth because the states can overlap a lot. And there is also a chance that you can get they form a single quantum state. In that case, we cannot really consider this HT as a perturbation term. And this Fermi-Coulton rule is not applicable, or this formalism is not applicable. So the situation that we work is the tunneling is weak and the states are relatively unaffected. Okay. Now this is the tunnel rate from one of the initial state to another final state on the other side of the tunnel barrier. Okay. Now let's calculate the total tunnel rate from the source side to the drain side. Okay. So that we can assume that the states from the source side, the states on the source side is a continuum. There's a lot of states in a continuous manner. Okay, and there are a lot of states available in the drain side also in a continuous manner. Okay, so the total tunnel rate is given by the integral T12 E square, that is the transition probability, transmission coefficient, and the rho 1 into Fe minus E1, this term, rho 1 is the density of states, and F is the occupational probability. So this term, rho 1 into F1, is giving you how many states are occupied on the source side. Okay, and rho 2 E minus E2 is the density of states on the drain side, and 1 minus Fermi function, these F's are actually Fermi functions, 1 minus this Fermi function is telling you the probability of those states being empty. For the transport to happen, you need to have filled state which is capable of donating electrons, and you need to have empty states on the drain side where they are capable of accepting those electrons. Okay, it's a product of those. Both of those need to be satisfied. Okay, so this tells you how many number of states to donate. This tells you how many number of states are available to accept, and this is the probability. Okay, so this is the total transition rate, and we work in the linear transport regime. What that means is E1 minus E2, the energy difference between two sides are actually far less than the Fermi energy. Okay, that means even though you have energy dependence for the transmission coefficient T and the density of states, but we are discussing a very small energy range where both of these you can assume to be independent of energy. Okay, we are working in the linear transport regime. That means it's just at the surface of the Fermi sphere where the variation due to energy is very small. Okay, that is where the transport is happening. Okay, so you can say that T12 and rho are relatively independent of energy, and you can take those two terms out of this integral out. Okay, so we can remove the rho 1, rho 2, both of them now we have assumed to be independent of energy, and the transmittivity T12. Okay, all these in together, I'm going to assume that it's a conductor, so tunnel wire at GT. Okay. Now what we have left with is only Fermi functions inside the integral. Okay. Now the total tunnel rate, when you remove these terms out of the integral, is gamma 1 2 is delta u by e square into gt into 1 by exponential delta u by kbt minus 1, where delta u is the energy gain, okay, because of the tunneling. Okay. Now this is applicable only in the weak coupling limit. Okay. The reason is the whole thing we can assume only in the weak coupling limit where the Fermi-Koldon rule is applicable. Okay. Weak coupling limit means GT is far less than E square by H. Okay. Where E square by H here is the conductance quantum. Okay. So if the E square by H is close to 1, then they are the same state, because it's one channel. It's connected by one transport channel. E square by H corresponds to the conductance of one transport channel. Right? To apply this formalism, you need to have E square by GT should be far less than E square by H. Okay. What that means is rho 1, rho 2 into T12 square should be far less than 1. But rho 1 and rho 2 are density of states. Okay. So in a nutshell, what this is going to tell you is T12 square should be far less than 1. That's what it's going to tell you. Okay. And at 0 temperature, this term gamma 1 2 is equal to minus delta u by E square into GT. Okay, where delta u of the energy gain, that is a negative quantity. Okay. Now that is the 0 temperature limit. When you apply 0 temperature limit, gamma 1 2 will have this value only when delta u is less than 0. Okay. You have to factor in the negative charge of electrons, which I have not assumed in any of this discussion. Okay. So once you substitute for negative charge, all these terms will fall in place. Now gamma 1 2 is 0 when delta u is greater than 0. That means there is no energy gain. Okay. So we have the expression now for the tunnel conductance at low temperature, that is this one here, from the source side to drain side, when there is an energy gain. Okay. And this is valid when GT, the tunnel conductance, is far less than the conductance quantum. But that means they are not connected by completely transmitting channels. That's what it means. Okay. Now let's assume what happens if you have voltage bias this tunnel junction. So you have the tunnel junction, which I have drawn in this shape here. What this says is tunnel junctions are leaky capacitors. If I draw the tunnel junction in this way, that's a capacitor. The capacitor has infinite tunnel resistance, RT. This is basically RT is infinite. But we have current going through, that's electrons going through the tunnel junction. That means these capacitors are actually leaky. Okay. So we have finite tunnel resistance and we have finite capacitance. Okay. So usually such tunnel junctions are represented by this symbol here. Okay. Assume that I'm actually voltage biasing this circuit with this tunnel junction. That means there is a voltage source. Voltage source will maintain the voltage across. Current source will maintain the current. Okay, that is the terminology. So in the event of Gt is far less than E square by h, we have delta U minus E into V. That's a negative quantity. And from the previous expression, we have, from here, we have gamma 1 to the tunnel rate is delta U by E square minus delta U by E square into Gt. So that is what it is. Okay. Gamma 1 is minus delta U E square by E square into Gt, or current is V into Gt, because delta U is minus EV. Okay. Or current is V by RT. RT is the tunnel resistance. Okay. So this is actually giving you Ohm's law, kind of Ohm's law back. Current is basically proportional voltage. That's current through the junction is proportional to voltage. Okay. But in this discussion, we have not assumed anything, any value to the capacitance here, or geometry here, or size here. We just have a tunnel junction. And what is the tunneling current through that? That roughly obeys Ohm's law. It works as a resistor. That is to condition in a really voltage, small voltage range, because all discussion happened assuming that transport happens in the linear range where the applied voltage is really small compared to the thermal broadening of the states. And transport happens on the Fermi sphere. Transport happens when you have really weak coupling. So all these things together, put together, the tunnel junction will behave like a resistor. That's what it says. It just justifies our assumption also. Okay, assuming attributing a resistance value to the tunnel junction. Okay, in the small voltage range, in small bias range, the tunnel junction will behave like a resistor. That's what it says. Now let us look at what happens when you have very small capacitance, or when you consider the charging part. Okay, in this case, let me assume that the junction is current biased. When I say current biased, means there is a constant current applied. There is a current source which pushes the electrons at a constant rate. The current is constant. It will maintain a constant current, or the current source has a very infinite, highly or very large internal resistance. Okay. One of the practical ways to make a current source from a voltage source is you just attach a very large resistor in series with the voltage source, then it becomes a current source. Okay. Because then the resistor which is in series is going to decide the current. That is going to dominate the whole transport. But of course, you have to make sure that resistance or resistor value, that the value of the resistance is really large compared to other resistive elements in the circuit. Then only that's going to dominate the transport. Okay. All right. So for this discussion, let's assume that you have a current source driving a current through this system. Okay. Now the electrostatic energy change because of the charge and discharging process, delta U, is the final energy minus the initial energy. So assume that you have adding an extra electron, that is a charging process. Okay. Then the energy difference between before and after is Q minus E, that is the final charge, and Q is the initial charge, and square of this charge divided by the capacitance is going to give you the final energy. Here square of the initial charge by the capacitance gives you the initial energy. So the difference here is delta U is this quantity here, E by C in Q minus E by 2. That's what it is. Okay. Now the tunneling is enabled only when you have the total delta U is negative, or there is an energy gain. Okay, that can happen only when this discharge, the condition Q is greater than E by 2, or V is greater than E by 2C. Then only you can get tunneling, or then only the tunneling is enabled. That is, when the Q should be, the tunneling starts when Q is E by 2. But the process of tunneling actually take the Q from E by 2 to minus E by 2, because tunneling is always discrete. This equation does not really assume that the Q is discrete. Okay, but every time an electron tunnels through, the change is by 1 electronic charge. What that means is, when the voltage climbs to E by 2C, tunneling happens, and it will bring the total charge back to minus E by 2. Okay. Then again, the charging will take it E by 2. Then again, another tunneling, then the total charge is going to be brought back to minus E by 2. And this is going to repeat. So, you have a charging process, then discharge, 1 electron. Charging process, discharge, 1 electron. Charging process, discharge, 1 electron. That is going to happen one by one. So, these are single electron charging process, because you have now a small junction with a very small capacitance, which enforces the voltage requirement given by this. Okay, E by 2C. Or the current runs through system only when this applied voltage is E by 2C or minus E by 2C in the negative direction. So it is going to look like there is a region in the middle where there is no current running through, voltage region in the IV. There, the transport is blocked. Okay. And when the voltage reaches E by 2C, the current is going to rise. Okay. And there, in this regime, immediately after the tunneling is enabled, the tunneling happens by tunneling of electrons one by one. One electron tunnels, comes back, the charge is going to flip, E by 2 from E by 2 minus E by 2, then again charging, next electron will tunnel, again flip, Q will flip to minus E by 2. This is going to go on. Okay. So the tunneling here happens 1 electron at a time, because the voltage that you have applied only satisfies that. For 2 electron, you have to put 2 E square by 2C, not 2 E by 2C or E by C. Okay. For that is not the voltage required. We are looking at the voltage which is in the vicinity of E by 2C. Okay. So this process where the electrons tunnel one by one is called single electron tunneling, or in short SET. And this happens at the period I by E. Okay. Now let's look at the energy time uncertainty here. So there is a temporal uncertainty of this tunneling that is of the order of the RC time constant tau RC. That is the fluctuation time when this tunneling is going to happen. Okay. So the period I by E, whatever the period here, that is accurate only to tau RC. So there can be a shift in this period of the oscillation. There will be a shift in the period of oscillation because of the charging discharging time. That is going to figure out as an uncertain time here. Okay, so within tau RC, the period of this oscillation, the single electron tunneling oscillation, is accurate only within tau RC. Okay, so period is accurate within the charging discharging time. That's what the message here. All right. Okay, so what we have discussed so far is quantum dots are small conducting regions where quantum mechanical effects are observed because of the confinement. These are small regions with really small capacitance, so the charging and discharging process of electrons require appreciable energy. But these energy scales are not really that high to observe these effects at normal temperature. So you need, most of the time, you need low temperature environment. Okay, and we also looked at this tunneling through single junction in the context of weak coupling between the source and drain using the Fermi-Golden rule and some simple mathematics following that framework. And what we found is this tunneling process through the junction happens one by one. Electrons tunnel through this tunnel junction one by one, which is going to set up an oscillation in the charge and also voltage across the junction. Okay, and these are called single electron tunneling oscillation. All right. Okay.